per award is to KLPT squared, algebraic pathfinding, and in dimension 2 and applications. And Thomas de Croo will give the talk.
Thank you for the introduction. So KLPT2, this is joint work with Wouter Castric, Peter Coutage, Abel Laval, Christophe Petit, and Jan Botti. I realized while making these slides that the title doesn't really say anything and it's probably a mystery to a lot of you. We'll be talking about isogenies. I'm aware that this is not the most approachable subject, and I'm aware that the doors are open, but I would still suggest to say seated because I've tried to keep this high level as possible so that everyone can follow. So the first slide, what's an isogeny? I'm assuming some of you may not even know that. An isogeny is rather simple. It's a map between elliptic curves. You can write books about isogenies, even without cryptography in mind. These maps have a lot of nice properties. The most important one, I guess, is that it preserves the group law, so it's nice. And in cryptography, we're also interested in the degree of the isogeny. What's the degree of an isogeny? It's simply the amount of pre-images that a point on the codomain has under this map. For example, this point has 3 pre-images, so this is an isogeny of degree 3. And this is sort of an invariant because then all the points on the codomain will have 3 pre-images, and we'll simply call this a 3 isogeny. I'll apologize for the experts in the room to slide some details under the rug. But maps can be concatenated, of course. So let's say we take this codomain as a new domain, and we compute an isogeny of degree 2, called the 2 isogeny. Then we have a concatenation of isogenies. This concatenation is very easy to see that it will be a 6 isogeny, so degrees multiply. Why? Simply because these 6 points get mapped to this 1 point. This is rather important in isogeny-based cryptography because we want the degree of the isogeny to be cryptographically large. So if you, say, concatenate 256 2 isogenies, then you already can start working in cryptography. And finally, maybe not super important for this talk, but isogenies have a dual. It's not really an inverse, but you can think of it as an inverse if you're not an expert. So you don't really need to draw the arrows, just elliptic curves are connected by isogenies of the same degree, and you go back and forth if you wish. If you prefer equations over pictures, this is what an isogeny looks like. It's not really scary, right? It's a 2 isogeny, it's a degree 2. You have a domain E0, you have a codomain E1, and you map points x, y to these rational expressions. You can also represent it differently with the kernel. Typically in isogeny-based cryptography, you'll represent it by a kernel generator. In this case, it would be 0, 0. Okay, so this is the geometry side. We also have the graph theory side. Let's say we're working over a fixed field, F241 squared. And we'll look at a subset of elliptic curves, namely the supersingular elliptic curves. There's 20 of them, I think, or 21 in this image. And we'll draw them as the vertices of a graph. And they'll be connected by these 2 isogenies, which you don't need to direct because of the dual isogeny. And then it looks like this. Now you may think, okay, this looks random, and you've made it look random or made it look hard, but actually quite the opposite. It's not easy to not have the edges overlap. But it really is, in a mathematically precise way, a random graph, if you wish. It's called a Ramanujan graph. It has nice expander properties. What does that mean? If you start from any given supersingular elliptic curve, you take a rather short walk in the graph, but you'll end up very quickly at a uniform random distribution as your ending point. We don't know how to maneuver in this graph, really, at least not efficiently. There's generic attacks, but both classically as quantumly, these are exponential. Okay, so at the geometry being the isogenies and the elliptic curves, this is the graph theory interpretation. And we also, given the title of this talk, we'll want to go towards the algebra side. For this, we'll need to know something about endomorphisms. Again, maybe a scary word that you don't know, but it's really easy, actually. It's just an isogeny with the same domain as codomain. And given how we're all at least a bit versed in cryptography, you definitely know some endomorphisms, simply the multiplication by k-map. Just pick your favorite integer, you multiply a point by that integer, and that's an isogeny, which happens to be an endomorphism. But there's a lot more. Let's say the complex multiplication map. Iota, for example, will map a point x, y on this curve to a point minus x square root of minus 1 times y. And this is also an endomorphism. And you can see that this a point xy satisfying the E0 equation, and point minus x squared minus 1y also will satisfy this equation. And then a final one, Frobenius map. Maybe in some other context people have encountered this. You can also take the p power of both your x and y coordinate. Given we're working over a field of characteristic p, this works, and any point satisfying the equation at the top will also have x to the p, y to the p satisfying this equation. But just like isogenies, we can concatenate endomorphisms, which is kind of cool. And the complex multiplication map does not have this name by accident. Why? Because if you apply it twice, it's simply multiplication by -1. If you apply Frobenius twice, it's simply multiplication by -p. And the odd thing is that endomorphisms don't commute. So applying Frobenius first and then this iota is not the same as applying iota first and then Frobenius. This is a bit weird, perhaps, but it's definitely believed that this non-commuting actually underlies the strength of isogeny-based cryptography. Now, some of you may recognize this structure, like I've seen this before in undergrad or grad school or whatever, and that's possible because there's actually a very strong categorical equivalence to some quaternion algebra. We're not going to be working with the quaternions over the real numbers. We're going to work with the quaternions over the rational numbers. We're going to add a base ijk. I squared is -1. That's pretty common. That's pretty normal. And typically, you're used to j squared being -1 as well. But in this case, we need to take -p. And then k is simply ij or -ji, if you wish. And there's an isomorphism between the endomorphism ring of supersingular elliptic curves and maximal orders in this quaternion algebra. It's always denoted BP infinity. If you don't know what an order is, it's basically a ring, if you wish, for simplicity reasons. And you can make several identifications, but obviously, like in this case, there's one obvious choice that you can make with just mapping multiplication by 1 to 1, mapping iota to I and Frobenius to J. In this case, we can then show that the endomorphism ring of the curve on the previous page is generated by these 4 elements. Now, this underlies pretty much all of isogeny-based cryptography. If I give you a random supersingular elliptic curve, not E0 because we know this one and it's easy, then it's supposed to be hard to find this O0. You can't do this. I mean, if you can do this, then you'll definitely have best paper somewhere, but then the field of isogeny-based cryptography is just dead. This just happens to be a curve that we know well. It has the invariant 1728 and so on. All right, let's go to KLPT. This is a paper from 2014 due to Courhel, Lothar, Petit, and Tignol, where Christophe Petit is also co-author of this paper. So on the geometry side, we had supersingular elliptic curves. On the algebra side, we have maximal orders in quaternion algebras. But what do isogenies resemble then? An isogeny has a degree, but that's the geometry side, but it is equivalent to some ideal. We call it a connecting kernel ideal, but just an ideal in the quaternion algebra. And recall it's not commutative, so it's a left ideal of the domain and a right ideal of the codomain. And the cool thing is this degree actually coincides with the norm of our ideal. You can see the norm as some sort of size as well, just like the degree. And this equivalence is called the Düring correspondence, which has been well established for decades. I think the 1940s, but I'm not 100% sure. And what is KLPT? KLPT is an algorithm that essentially says, well, if you give me such an ideal representing some isogeny in the geometry side, but we're working in algebra side, I can give you an equivalent ideal because they're only unique up to some equivalence, but it will have different norm. Now, if you translate this back to an isogeny, that's pretty cool. Why? Because there's no reason to assume that an isogeny, which has a degree a power of 2, should have anything to do with an isogeny of a degree a power of 3. But on the algebra side, we can make this happen simply because it's apparently easier to work with the algebraic version of isogenies. This is used in, for example, SkiSign, which is in the NIST submission, although there are higher dimensional versions now which actually can bypass this completely. It can also be used constructively, which is not unimportant, namely given a maximal order O, we can actually construct an elliptic curve with E in polynomial time. Recall that the opposite is not true and is the underlying hard problem. Given E, we cannot find O. So this can be used as a one-way function in any cryptographic protocol that you wish. There's a small thing to remark, though. There should be an ideal of size P. The best that we can find is P cubed, unfortunately. And this paper is over a decade old, and we've gone from P to the 3.5 to P cubed. So that's not a massive improvement. So the question is, like, can this be improved upon? Okay, so this is the one-dimensional version, and given the title, we're going to try to up this to dimension 2. But what's an elliptic curve in dimension 2? It depends. There's two options. It's definitely called an abelian surface, but it falls into two categories, namely a product of elliptic curves or a Jacobian of a genus 2 curves. The first one is rather easy, just like you would make a plane out of the x-axis and the y-axis, really just component-wise. The second one is a bit more tricky, but if you know an elliptic curve, it's a genus 2 curve, so it's not much different. This is a geometry side. I'm not going to write down equations for isogenies in dimension 2 because they're just more elaborate with case distinctions. There's a similar graph theoretical structure behind this, but again, it's just a lot more edges, a lot more vertices, so it would not be that helpful. Instead, we're going to jump to the algebra side immediately. So in dimension 1, we had elliptic curves, which are maximal orders. And in dimension 2, we have abelian surfaces. There's a lot of words here on this slide. The most important part is we have 2 by 2 matrices. So these matrices SR conjugate RT, these are what will represent our abelian surfaces on the algebra side. There are some conditions on there, like this matrix needs to have diagonal elements, which are positive integers. It needs to have determinant 1 and some equivalence relationship. But essentially, we're working with 2 by 2 matrices. Okay. So abelian surfaces, special 2 by 2 matrices. What's the isogeny equivalent then in algebra side? Again, 2 by 2 matrices. This time we're going to call them gamma, and they have to satisfy this condition. If you are given 2 abelian surfaces in algebra form, G1 and G2, and you want to connect them by some isogeny in algebra form, then you need to take G conjugate transpose multiplied with gamma conjugate transpose multiplied with G2 times gamma. And then it's n times some G1, which is also given. The degrees are, you also have degrees, obviously, in dimension 2 for isogenies. And then you may wonder, okay, 2 by 2 matrices, like you can take the determinant and you'll have the degree, except we're not really working with elements in our matrix which commute. So what's the determinant of a 2 by 2 matrix? Is it A times D minus BC or A times D minus CB? So you need to take the reduced norm of this gamma, which is the calligraphy n. I'm not mistaken, that's the norm of the Dieudonné determinant, if you wish, if that says anything to you. But again, we have some notion of degree on the isogeny to like some notion of norm on our 2 by 2 matrices, which represent these isogenies. And this is then the main theorem of our paper, KLPT2. It says that if you are given an input, 2 input matrices, G1 and G2, representing these abelian surfaces, and you are given a prime number, typically you will want L to be 2, actually, or maybe 3, but not much larger. Then under some heuristic assumptions, we can actually find such a connecting matrix gamma, which represents an isogeny. Again, information theoretically, we expect a solution to exist linear in P, and we only found a solution which is P to the 25. So it's far from optimal, but it's still workable. Small remark, if you really want, you don't have to work with a prime power. Generically, you'll want to, because in dimension 2, isogenies of degree 2 are easiest to work with. But you can replace it by a power smooth integer as well, if you wish, for whatever application. Okay, so the proof, I think, is about 12 pages in the paper, if you want to look it up. It's a lot of lemmas, a lot of propositions. I'll try to condense it in a sketch of the proof on 2 pages. Why? Because at a certain point, this has nothing to do with isogenies anymore, right? This is just an algebra equation. You can give this to a mathematician who works with quaternion algebras, and he may say like, oh, I can try to solve this. Like, doesn't even have to know this Ibukiyama-Katsura-Oort correspondence. So you are given a G1 and a G2, and you need to find some gamma such that gamma conjugate transpose times G2 times gamma equals G1 up to some power, up to some factor L to the E. This E can be anything, and L is typically 2. The first observation was, well, let's say we don't have G1 and G2, but let's say we have H1 and H2, and for some reason their upper left entry is equal already, so D. I forgot to add here that H1 and H2 also need to have the same determinant, and in this case the determinant is well defined because D and T1, T2 are integers, so this is uniquely defined. But let's say we are given this as input, and then we can easily solve it because this tau actually works as gamma. You can calculate this, and we have a solution. So that's pretty simple. Obviously, we would not be so lucky because this top left entry will be the same with negligible probability. But we do have a new goal to transform these G1 and these G2 into H1 and H2 so that we can actually apply this tau, if you wish. And then we'll just say like, oh, this D needs to be a power of L because that's what we're actually after. Okay, how will we do this? Well, you can show that you can do this by transforming this G, multiplying it on the left with U conjugate transpose and on the right with U, where U is a matrix with reduced normal power of L, such that the top left entry of U star GU is also a power of L. Okay, let's take an arbitrary matrix U. Let's see how it goes. A, B, C, D. These are elements in quaternion algebras. These are not just integers or something, but it can be anything. It doesn't need to have a specific determinant or norm or whatever. And let's just focus on one G. I've removed the subscripts. You can add them if you wish. The noteworthy thing is if you calculate this, we're interested in the top left entry of the product U star GU. But as you see, B and D vanished from this expression, right? This is quite nice. You have the norm and the trace, but whatever B and D are not there, which lead to the following strategy. Namely, well, first we'll need to find an A and C such that this expression is a fixed power of L. And given those, we still have freedom to find values for B and D such that the reduced norm of this matrix is also a power of L. So due to this freedom of like the second column of U not really being part of the top entry, we can split this up into 2 pieces. And then the solution is most clear if you take the second one first, the second condition first, and that's a Diophantine equation, but it's actually completely equivalent to one-dimensional KLPT. So we know how to solve this. That's pretty cool. And we have algorithms for that. And the second one, the first one then, is a multi-step algorithm, which I'm not going to explain here, but it involves a lot of steps. So there's quadratic forms, there's some lattice reduction in dimension 8, and so on. And this results in an output of size p to the 6.5. This is a sketch of the proof, and some people may be thinking, okay, you had p to the 25, and these numbers don't add up to 25 in any way, shape, or form. But the KLPT, you need to apply twice, and then it has another factor 2 impact due to taking the norm. So the p cubed is actually a p to the 12. And similarly, at the second step, p to the 6.5, actually, due to taking the norm, also has to be doubled. So that impacts it with a factor 13. And then 12 plus 13 actually adds up to 25. Some other things that we did also was converting between isogenies and matrices. So on the algebra side, you have these matrices representing isogenies, but there's no real dictionary to translate between them. So if you have a matrix representing some n-isogeny, we can actually decompose this now in polynomial time as a concatenation of isogenies. Ideally, we want n to be smooth, power smooth, or whatever, so that we can actually work with it, because computing high prime power degree isogenies in dimension 2 is hard. And this actually leads to a constructive version of the 2-dimensional Döring correspondence, which we call the Ibukuyama-Katsura-Oort correspondence. Namely, if we're given a matrix G, so representing an abelian surface, we can actually realize the abelian surface. It can be a Jacobian of genus 2 curve or a product of elliptic curves, but we can actually write it down. Again, the opposite we expect to be a hard problem, namely given an abelian surface, you are not able, or you should not be able to write down this matrix G. The opposite is also true. Given chain of isogenies, again, preferably power smooth norm or prime power norm degree, can actually compute this matrix in polynomial time representing this isogeny. So we have a pretty nice dictionary between the algebra side and the geometry side. Both of these were in Chu's PhD thesis, one implicitly, so not written out in full detail, and the other was sub-exponential, but we managed to improve that to polynomial time. And as final application, what we did was we attacked, well, one of the applications was that we attacked the Charles-Gordon-Lott hash function. If you don't know what that is, essentially pick any starting abelian surface that you wish, A, you compute some isogeny, doesn't matter how, as long as it's deterministic, based on the input message, and then you end up in some other abelian surface, A prime, as codomain. You can then output this A prime or some invariant of this A prime, doesn't matter, and this is a hash function. It also works in dimension 1. Well, we can attack this with our knowledge from KLPT2. We can actually make collisions based on this. It assumes knowledge of the matrix G corresponding to the initial node. Okay. Now you may think, well, that's the hard problem, right? Like, you don't have to have this knowledge. Why can't you just write down an abelian surface for which we don't know the G? This is actually a hard problem in isogeny-based cryptography. We cannot do this. We need a trusted setup. Anytime you want to create a supersingular elliptic curve or a super special abelian surface, we will know in the elliptic curve case, it's endomorphism ring O, or in this case, the 2x2 matrix G. There are no known ways to find the starting node for which we don't know the G, unfortunately. So as final slide to conclusion, this is what the biggest contributions were from our paper. And maybe more interestingly is future work. Applications, we can generalize some one-dimensional isogeny-based cryptography things if you wish, but maybe the most interesting part is improving this bound, because an isogeny of the p to the 25 is kind of large if you're expecting that theoretically one of degree p should exist. So if you want to work on this, I would suggest to look at this and try and improve this bound. Keep in mind that if you can just improve KLPT in dimension 1 to like p to the 2.5 instead of p cubed, then you're already improving this bound as well, because we use this as a subroutine. All right, this is the ePrint version of the paper, and I'm happy to answer any questions. Thank you.
Questions? Okay, I have, did anybody have a question there? Okay, oh.
Significance of the bound. What is the practical significance of a bound of p to the 25 versus p? Where does it make a big difference?
So the bound is not on the running time, it's on the output. So the output of your isogeny is p to the 25. And if you just consider it, let's say you do a power of 2 isogeny, in practice, there's some divide and conquer algorithm that's going to make it slower by a factor 25 log 25, I would say. So it's like 30 times slower than it theoretically should be.
Okay, but not a huge factor.
No, because you can like split up your isogeny into smaller pieces, so it's not that significant. I mean, it's still practical. In dimension 1, you also had p cubed, and that was still used. And that we're talking about, well, I'm not sure, less than a second at least, whereas you can then maybe expect it to be 50 milliseconds instead of 150. So it's not impossible.
Any other questions? So I have a quick one. So I think I missed something. So when you stated your main theorem, your algorithm, you wrote that this works under some heuristic assumptions. And what are these? I didn't
Oh, there's quite a few of them, like some, it's in the proof of like, yeah, most of them are in this multi-step algorithm where you have some assumptions based on coprimality and on some shortest vectors in lattices that should exist and so on. So there's a lot of assumptions there hidden, but in practice, we never really encounter issues.
I see. So this is not hard. It's like a assumption that like some unproven lemmas that you assume. Is that it?
No. This is not, not at all, no. This
So-
is just, we assume that it behaves random, even though it may not be the case.
I see. I see.
Yeah.
And okay, got it. Okay,
Yeah.
got it. Okay. Any other questions? Okay. Thank you very much, Tom.